Good day, everyone. You are welcome to Master Lucas Academy, and today we are going to be looking at what we call the Joule Thompson effect. Now, when we're talking about the Joule Thompson effect, a scientist known as Joule Thompson worked on how temperature and pressure affect the nature of a given gas when it undergo what we call adiabatic condition. Okay, so the Joule Thompson effect is the phenomenon of change in temperature when a gas is made to expand, okay, adiabatically from a high pressure region to a low pressure region. Now, with respect to this definition given here, now we have what we call the coefficient of Joule Thompson. This one here represents what we call the coefficient of Joule Thompson effect. So since the Joule Thompson effect has to do with the what? The change in temperature with respect to the change in what? In pressure. Okay. And in this place, we have the enthalpy is being kept constant there. So because of that, then there are different forms in which Joule Thompson effect has affect the nature of gases. Okay, so when it expand adiabatically from the high pressure region to the low pressure region. Now this include if the coefficient of a Joule Thompson effect is positive, then positive expansion causes cooling. So when it is positive, then positive expansion causes what we call cooling there. Now for the next one, if the coefficient of Joule Thompson equals to negative, so the negative expansion causes what we call heating there. Okay, so in a situation whereby the Joule Thompson effect is equal to 0, so neither cooling nor heating occurs. That is, neither cooling nor heating is taking place. Now we have to talk about what we call the inversion temperature. Inversion temperature Ti. Now, what is inversion temperature? The inversion temperature is the temperature at which the coefficient of Joule Thompson effect is equal to 0. Take note of that. So this particular one is what we call the inversion temperature of the what? Of the gas. Now, with respect to the one that we have here, we can here at 300 Kelvin, at 250 atmosphere, Joule Thompson coefficient is 0.173 Kelvin per atmosphere. If a Joule Thompson expansion is carried out from a pressure of 50.0 atmosphere, so this 50.0 atmosphere that we are seeing here, this is the high pressure region for it, to a pressure of 1.0 atmosphere. Estimate the final temperature if the inertial temperature is equal to this one here. So we are going to use this formula using the Joule Thompson, where we have this Joule Thompson equals to differential of pressure, the differential of temperature rather, over differential of pressure, then followed by the constant here. So with respect to that, we are going to go in this direction. So we are going to be looking for the temperature change. So temperature change is T1 minus T2 rather minus T1 over P2 minus P1. So from what you have in this place, still equivalent to this. Now, from what you have here, the coefficient of Joule Thompson is given to be this. So here we are going to have 0.173 equals to, now they said if the inertial temperature is equal to this one here, so that means T2 minus our T1, which is what, 300, all divided by, now our P2, from that question, our P2, if you look at what we have here now, this is the first mentioned pressure there, and this is the second pressure. So that is 1 minus 50 there. Okay, so with respect to this, here we go. We are going to have, you cross multiply, that will be 0.173 into bracket 1 minus 50 equals to T2 minus 300. Now, if you subtract this 0.173 into brackets minus 49 equals to T2 minus 300. Now, with respect to what you have in this place, minus 300. So arithmetic says when this cross like this, it will give you plus 300 equals to T2. So the next thing that will happen here, Kelvin. So that is our final answer there.